At 7 a.m. on a Tuesday morning in 2026, a robotic arm precisely places a coffee mug on Alex's nightstand. In this world, the presence of autonomous machinery isn't a spectacle, it's a mundane utility. This domestic helper relies on three specific systems to function. First are the manipulators, the physical structural links of the arm. Then come the actuators, the motors acting as artificial muscles to drive movement. Finally, the controller, the microchip brain that processes every action. Integrating a machine like this into a home used to be impossible. Early industrial robots were blind and reactive. They followed rigid, repeating sequences and had to be locked inside steel cages to prevent them from crushing any human who stepped into their path. This hardware evolution began with the 1954 Unimate. As the first programmable industrial robot, its heavy metallic structure and hydraulic power meant it was built for the factory floor, not the living room. Yet the concept of these workers predates the technology by decades. The word robot was actually coined back in 1920, appearing in a science fiction play by Czech writer Karl Čapek. So how did we get here? How did we turn blind, caged iron into the safe, intelligent partners navigating our cities and homes? As Alex leaves for work, the environment gets significantly more complex. A city street is an unpredictable obstacle course that a robot must learn to read in real time. Autonomous vehicles perceive this space through sensor fusion. By combining cameras with radar and LiDAR, which uses light to measure distance, the car creates a three-dimensional map of every pedestrian and vehicle in its vicinity. But seeing the road isn't enough. The robot has to decide how to move through it. This requires a mathematical approach called sampling-based path planning. One common method is the rapidly exploring random tree. The computer randomly branches out thousands of potential paths from its current position, searching for a sequence of connections that reaches the goal without hitting an obstacle. This calculation happens in milliseconds. If a cyclist suddenly swerves, the computer instantly collapses the old plan and redraws the path to avoid a collision. Autonomy is the result of turning unpredictable physical spaces into solvable math problems, updated dozens of times every second. At the workplace, the challenge shifts from navigation to manipulation. In a warehouse, robots must handle parts and packages that aren't always in the same place. Older systems relied on proportional integral derivative controllers and strict linear code. These worked well in a static factory, but if a part shifted even an inch, the entire program would fail. Modern machines are designed to be much more flexible. This is the Boston Dynamics Atlas, an enterprise-ready bipedal humanoid engineered to move through the same dynamic workplaces humans use. The software breakthrough here is reinforcement learning. Instead of following a script, the robot learns through a reward system. It takes an action, receives a negative signal for a mistake, and a positive reward for reaching the goal. It refines its own behavior through trial and error. This intelligence is scalable. Once one robot learns how to handle a difficult object, that behavior can be redeployed across an entire fleet simultaneously. We are no longer limited to writing rigid instructions. We are training robots to adapt, which finally allows them to work alongside us without those safety cages. There are some places where even intelligent software isn't enough to ensure safety. In a hospital, robots must physically touch fragile human patients. Traditional joints made of steel and high-torque motors are inherently risky in these settings. Even a small error in force calculation can cause injury. This is why researchers are developing soft robotics. By using pneumatic actuators made from silicone and rubber, these machines use their compliant structure to handle delicate objects without high-pressure force. True integration into our lives requires machines to adopt the physical compliance of living organisms, ensuring they assist and heal rather than harm. By the end of the day, Alex has interacted with a dozen autonomous systems. When machines can handle the driving, the manufacturing, and even the healthcare, the question moves from how does it work to where do we fit in? The shift toward automation brings real social pressure. As machines take over repetitive physical tasks, we face legitimate concerns regarding the de-skilling of the workforce and the displacement of manual labor. But the technical limits of these robots reveal their true role. Algorithms struggle with ethical supervision, genuine empathy, and solving nuanced, unstructured problems that don't have a clear mathematical reward. This points toward a hybrid ecosystem. As shown here, we are moving toward a future where a fleet of intelligent machines handles the high-risk physical execution, while humans maintain the strategic and moral oversight. The history of robotics isn't a story of replacement, but of offloading. By delegating the rigid math of navigation and the physical strain of labor to these partners, we are carving out more room for the creative and empathetic work that a machine cannot calculate.